Hello everyone, my name is Annapurneswar Putrevu. I'm alumni of NIT Rai. I graduated in year 2003 and I have total 22 years of software experience in IT industry. Overall, I have been working on different technologies all my career, starting from Java JD to middleware technologies and now to the cloud applications. Today we will be, and yeah, thanks to Conf42.com for giving me this opportunity to talk about self-healing data pipelines, right? So, what is the problem statement which we are trying to solve? So, what is the growing challenge we have? Over the period of time, earlier back in days, we used to integrate applications, right? So there was a data transformation, data integration happening different applications. But of late in this AI world, now we see that there is sudden influx of data. Data is the key now, right? All stakeholders are looking for data. They want to build visualizations, they want to do some sort of analytics. There are some machine learning models which you want to train on those particular data sets. So there is sudden influx of data from all the corners, and data engineers build data pipelines day in and day out, right? In a very high magnitude. The problem here is if something gets broken in the pipeline, then how do we make sure that the pipeline is back working properly? Because there is a downside of it because it affects our stakeholders to take key business decisions. So to address this, we traditionally what we have done is we always used a rule-based systems, correct? So we say that there is a rule saying that if the CPU percentage is this much higher, then add a new node or stop the server or restart the server. If a system is hanged, then restart the server. If there is a network failure, then do something else, right? And throw an alert or send an email alert to the users, right? So this is what a traditional rule-based system does, and it is basically static in nature. Main critical pain points what we have seen over the period of time is the schema drift, right? In a typical data pipeline, obviously, just to oversimplify it, you have a system source and a system target. You want to get the data from source to the target system. Now you built your data pipelines on particular schema, and then suddenly over the period of time, the schema has changed for some reason, right? Obviously, your pipeline, your ETL transformations, whatever you've written, might break because of the schema drift. And suddenly the data pipeline is broken, and then you get an alert, and then you go and try to fix it, and then rewrite that whole transformation with the new schema. This is called the schema drift, right? So these are the pain points. So basically, it again brings down your system, and then there is a loss of business hours there. The another problem is resource contention. Different in entire pipeline, you might have your Airflow DAX working in the background, in glue jobs working in the background, or different virtual machines working in the background to process the data. And due to sudden influx of data, the resource is not capable to handle that data, right? And the system goes down. So that can be one of the pain points, and that happens quite frequently, right? Even sometimes your data warehouse tools may not be able to handle the queries, the ETL transformations, inserts and insertion data into the tables, or data visualization queries coming and hitting to the database server. There can be so many issues there. And then there are system anomalies, obviously, right? There are unseen errors, there is network failures happening. So these are the typical critical pain points of a typical data pipeline setup as in today. The limitations we already have discussed, right? The limitations of current approaches is it is very rigid. You define a rule, you say if the CPU percentage is this much higher, then you do something to fix it, correct? And you, if there is certain deflection, there is no rule for that, and then you're not able to solve that particular problem. Another problem is unable to adapt to new failure patterns, right? There will be constantly new failures happening, and you might not have written rules to take care of that, right? Obviously, high maintenance because there is a manual intervention required, there is a downtime required, and to do the rule updates, and obviously poor performance in some complex scenarios, right? We enterprise scale data operations demand more intelligent and adaptive solutions, right? And that's why there's a new paradigm shift, which is like autonomous self-healing. So what if the pipelines self-heal themselves, right? That's a thought which we should think on. So what the paradigm shift is, moving from reactive to proactive, right? And basically a policy driven framework, and then through intelligent prompt engineering we can actually implement this autonomous self healing, right? So there are two three concepts which you might use here. One is definitely called as reinforcement learning. You can use machine learning for checking anomalies. You can have reinforcement learning, and you have these agents which can actually think of it like your twins who can actually go there and then fix the problems automatically for you. So that is what this RL agent is all about. And then you can do prompt engineering, you can get this data, vectorize it, and then you can use any agents, agentic AI, right? And then develop some flows and then query the database in the backend, and it cannot or obviously it will give you the information of what actually went wrong into the systems, right? So how these RL agents learn this resilience, right? So basically these RL agents or reinforcement learning agents, they observe this pipeline telemetry data. So what we do is we gather the data of all the systems in that entire pipeline. So the pipeline can be your orchestration tools. Let's say I'm just taking example of Apache Airflow, right? Or a glue job in AWS, or a Lambda function in AWS, or any virtual machine, how it is performing, right? So those telemetry data you can, and then you have your data lakes and your data warehouses. So whatever systems are there into your entire pipeline, you can actually collect them, collect the metrics data, the telemetry data, right? So what is the resource utilization, what is the error rates, and what is their system health. You can capture all this information and repeatedly through trial and error try to discover the best possible way to handle that error scenario or that failure scenario. This is what a typical RL agent would do, right? The agent basically learns dynamically, adjusts the resource allocation. It can reconfigure the TTL workflows, apply corrective actions if it has to. It can do schema mapping in case of schema drift. It can do some intelligent retries like exponential backoff, something like that, and then put some adaptive back pressure before failures cascade. So this is how this typical RL agent would work. The framework architecture for this is definitely important thing is you need to collect the telemetry data of your system, right? So historically, whatever telemetry data is there, you can collect in AWS. If you talk, you will have your CloudWatch metrics and all that stuff, and then continuously stream these metrics, and then using cumulative fault data you can develop a comprehensive learning on top of this particular data, right? And then once you get this particular data set, then you can do your reinforcement learning agent training, right? Continuously these agents will be looking at the metrics data, and it will identify the patterns, it will identify the failure scenarios, and it will try to fix it through autonomous response, right? Then real time these agents can take a corrective actions, including resource allocation, right? Spin off another node or drop one node, do some sort of workflow adjustments. It can do all that stuff. So this is a typical framework architecture. We already talked about just now about the prompt engineering for intelligent prompt engineering for pipelines, right? First thing first is you can actually go and then put a prompt onto the system saying anomaly detection prompt, right? Using your natural language query. You can say, hey, tell me, like, from past 24 hours, what is the CPU utilization of my system? Or how many errors this Airflow DAG has been throwing from past couple of hours, and then it can give you an anomaly based upon that, right? So you don't need to go to a dashboard and click on it. You can just do some intelligent prompt engineering, and then you can get that information at your fingertips. After you get that information, and then you can also ask, hey, okay, these many machines have been failed, can you tell me what is the root cause? And that prompt can actually trigger some agent which can actually try to figure out. It would go and read the logs, the traces and metrics, and pinpoint exactly what happened with respect to and it will give you contextual explanations based upon your anomaly detection prompts, right? And then you can also say, okay, you can instruct it because now you know what is a problem. And then being human, you have that intelligence power. You can just say, okay, go and spin off another instance, EC2 instance, for example, or spin off another node or spin off another worker node in Redshift or something like that, right? And the agent can go back and actually do that task for you. So definitely this prompt engineering is an added advantage now in this today's AI world. We can take use of marvelous, amazing LLMs, and we can put LLM, we can trace the data in the database, and you can build your quick agentic flows on top of it, and you can actually automate this entire process. And then, yeah, a typical process flow of a data pipeline would look like this, right? I'm just taking example of Oracle database. Think of this as an external source, right? This is not part of the part of your pipeline. And then you have DMS, data management service in AWS, right? It constantly pulls the data from the database using CDC technology, and then it has the schema information, and then Airflow DAG kicks in, and then it basically does the ETL, the pre-processing and post-processing of that particular data set. You can have glue jobs as well. And then you put monitoring layer on top of all these nodes here in a typical data pipeline. After this, it will be going to the Redshift and data lakes or data warehouses. I'm just using it can be Snowflake, anything, right? And then typically there will be a monitoring layer on top of all these applications wherein it will be collecting the data. And then there will be an anomaly detection layer, which is you can use a typical machine learning algorithm like isolation forest algorithm to do an anomaly detection continuously on the data, on the monitoring data. And if you find any problem, then automatically RL agents will kick in and do the self-healing actions like restarting the server and then giving the feedback like what exactly, once that RL agent does it work, it can give a feedback that, oh, the system has been started and it has been working fine, or system is not working fine, still it is having some trouble. So this is a continuous loop which it will go into, right? So this is that called a feedback loop, right? So this is a typical flow of RL agent based self-healing data pipelines. So what are the layers which will be used to implement this? One thing is the monitoring layer, right? As I said, continuously track the pipeline health, resource usage, data quality across DMS, entire monitoring layer. I'm just taking an example just for you to understand what are the different components in data pipeline in AWS setup for Azure and for GCP or for your proprietary data pipelines, it can be different. And then you have this analysis layer. You can use machine learning algorithms. As I told, isolation forest algorithm is really great. It can actually figure out what exactly that anomaly is, what is the resource bottlenecks, what are the data inconsistencies, and it can trigger an alarm. When alarm is triggered, there is another layer which will be that RL agent layer, which will evaluate the pipeline state and select optimal recovery actions. Example is rescheduling the jobs or scaling the glue resources or remapping the schemas or retrying the DMS loads. And then you have your execution layer wherein automation of engines implement recovery actions across AWS services. So it will be executing those decisions what your RL agent has been taking, right? Minimizing the downtime or manual intervention might be required. If not, it's not fixing. Then there is a feedback layer, then aggregates, it basically executes the action, and then it also sees whether that action has been properly implemented and it is giving the desired results or not. And this is for our agents for its continuous improvement, right? So we talked about this whole reinforcement learning, machine learning and all. I just wanted to take an opportunity for the people who doesn't understand reinforcement learning, and probably they understand machine learning and AI and all that stuff. It's kind of machine learning, but little bit different in the sense like in machine learning you have independent variables, you have x and x variables like all the attributes, and then you have a dependent variable which is y, which is a target variable, and your job is to predict what the target variable will be, right? But in reinforcement learning, that x which we're talking about the independent variables, think of it as a state, right? That entire row, you can think of it as a state, sorry. And that state consists of this whole matrix. Like for example, it will say schema mismatch, right? What action can be taken to solve that particular problem, or what is a metrics there? Is there a network latency? Is it a mismatch of the attributes? Those kind of data sets, they will be there. Like it can be, the columns can be error type, what stage it is, what is the latency, right? These can be its attributes, state attribute. And then there will be one more, you can think of this as a tuple: state, action, reward, and next state. You can think of as a tuple, right, in Python. So action is like on this particular state, right? The state is like there's a timeout in the transformation, right? So the system is down. So what action would we like to do? Probably want to retry. So that is the action which you'll be taking. Example, restarting the task, right? And then once the state you saw, you took an action, then there is a reward system. The reward system is basically how good a job you did, right? And think of that your professor is giving you extra marks for actually doing a good job and is punishing you for not doing any good job. So this is very critical, and I'll explain you in a bit why reward is very important. And then there is a next state. So once you take a state, you took an action and you get a reward, obviously it will transition to a next state. So this whole quadruple tuple is the key of reinforcement learning. This is the data structure which it will be using, right? I just gave an example of the data, right? So the state can be having error type, action taken, stage, and latency, right? So these are the attributes which will be going into the reinforcement learning models. And then you specify the rewards. If you say that if the next state is healthy and you did this, so you say +1. If the next state is not healthy, you probably punish it, or you basically will say that you have not done a good job and probably you give a -1 to it. Same way, there is a timeout. Transformation is the action taken and the latency is 2 seconds, and action taken is retry, the reward is 0, right? You are not doing it again because it timed out again. So you are basically punishing to the action you have taken, right? These values are nothing but called as Q values, and this is what drives everything in reinforcement learning. It basically looks at that Q values. It maintains a Q table, and for each and every action, it actually looks at that particular Q table and applies the rewards, right? And it's a continuous process. The goal of any reinforcement learning program or the agent is, given a state, what action should I take to maximize my long-term reward? So the more the rewards, the more the reinforcement learning agents understand that if I do this way, I'll be rewarded, and then this is the right way to solve particular problem, right? Now, what is the key capabilities? It's like real-time monitoring, continuous pipeline performance will be tracked. Your dynamic resource management can be done, right? Intelligently, you can reallocate computational resources based on current demand. ETL workflow optimizations can be done, right? If the ETL is taking a lot of time or it is not working up to the mark, then probably your ETL processes can be adjusted. It can even do schema remapping. How schema remapping? It can crawl over the source schema and figure out what the schema is, then apply those using those schemas back to your ETL using some LLMs in the background, and then it does automatically schema deployment and it automatically remaps the schema, and then through CI/CD it automatically deploys that particular solution into the server. So how cool it is, right? So these are the things which agent will be doing once it figures out that this is a problem statement. Advanced response mechanisms also there, like targeted retries, exponential backoff, right? So what is exponential backoff? You want to retry, but you're continuously retrying after every 30 seconds. You're not doing good because you're choking that whole pipeline, because obviously the target system is not up and you're still making a call and you're bombarding with the request. So you're choking with your request, right? So ideal thing is you do have exponential back off, right? 30 seconds now you did, maybe after after 2 minutes you try, maybe after 10 minutes you try. So this way you're not choking that entire network, right? With your request to the server. Dynamic flow control can be also done to prevent system overload, which is like a throttling of your data ingestions, which is called adaptive back pressure. You can do resource reallocation automatically, like automatic scaling, and then you can do some workflow adjustments, right? Deployment, you can use Kubernetes based or ECS, it's your wish, and you can containerize this particular application, and then you can deploy it to any cloud based application, not a big problem there. Evaluation, how do we evaluate your methodology, right? Testing conditions. Best thing is, first of all, you need to figure out how to get the data, gather the data, and simulate that whole error scenarios, good scenarios, bad scenarios. Probably you should create another environment, and with simulated data, you know you can create these situations and then evaluate whether your RL agents are working appropriately or not, right? Yeah. These are the key metrics like we have seen over the period of time. By doing this, use response speed is 3x, your service level objectives are like 94%, it's improved, and mean time to recovery is like drastically reduced. System benefits, obviously, it is we are moving from reactive to proactive data pipeline management with learned optimized strategies, autonomous self management, less human intervention, and enterprise scale capability, right? It can scale to any sort of magnitude of data pipelines you have set up. It is continuous policy evolution. At the end of the day, RL agents come up with a policy, right? And it never stops. If a new pattern comes up, again, it reads it and it tries to solve that particular problem. This never stops. So it has this continuous policy evaluation strategy. If you want to build your self-healing pipeline, what need to do, right? Like basically deploy comprehensive observability across your pipeline. Stack matrices, logs, traces, which should be used to feed that RL agent. You can create a simulation environment, right? Build a framework that mirrors production, as I told you, and then define recovery actions. Like you need to know that if this is a problem, this can happen. So you need to have your actions, what action should be taken, because again, this has to be put into the reward system. Remember, that's why, right? And deploy and iterate. Slowly go, don't go big bang, right? Probably you just try to solve one problem at a time and then add one more problem and then add one more problem. Now, rather than going with a big bang approach, probably you are just looking for schema drift for the time being, or probably you're looking for resource contention, and then you can add for network latency and stuff like that. So what is the future? Intelligent and adaptive integration. So self-healing pipelines represent a fundamental shift in how we architect data infrastructure. By combining RL with prompt driven intelligence, we create systems that don't just fall gracefully, they learn, adapt, and evolve. So basically, we are shifting from reactive troubleshooting to proactive policy driven resolution. And yeah, thank you so much. Thanks for listening to the presentation. And you can reach out to me in LinkedIn if you have any questions or anything about it. Thank you so much.